Welcome to the deep dive. Today we are really plumbing the depths of a paradox. It's the kind that sits right at the foundation of, well, modern scientific thought.
Right.
We're talking about Johannes Kepler, a towering figure. His name is rightly synonymous with the true mechanical laws of planetary motion.
Absolutely. Foundational stuff.
But here's where the story gets really interesting, I think. The most revolutionary physics-defining work Kepler ever did.
Mm-hmm.
The work that really set the stage for Isaac Newton, it actually emerged directly from what you could argue was the most spectacular, beautiful, theoretical failure of the early scientific revolution.
It's an incredible story. A beautiful failure. That's a great way to put it.
It is, isn't it? It's just a stunning, almost agonizing example of how scientific truth is often found, not through one clean leap, but, through a process of gorgeous but ultimately incorrect guesses.
Yeah, the messy path to discovery.
Exactly. So our mission today, and we're guided by the sources you shared with us, is to unpack that strange and really critical journey. We're kind of traveling with Kepler from this mystical world of ancient geometry and divine harmony all the way to the messy, high-resolution reality of elliptical orbits.
Yeah.
Our core goal is to understand that cognitive leap. How did Kepler move from fervently believing the universe was constructed using only 5 perfect shapes?
Which sounds wild now.
Right. To defining the exact, mathematically precise, mechanical motions of the solar system.
And that contrast, it just gets right to the heart of what the scientific process demands, doesn't it?
It really does.
What we're exploring here is the intellectual and, frankly, the deeply personal journey of a man who believed, with every fiber of his being, that he had found the definitive mind of God expressed in simple geometry.
That's intense.
It is. And that tension between theology, his faith, and observation, the data, it drove his entire career.
So to really appreciate the shock factor of where he started.
Yeah, you really need to grasp the audacity of this initial idea.
Right.
Kepler initially proposed explaining the entire architecture of the cosmos, and we're talking specifically the precise spacing of the 6 planets known then.
Mercury, Venus, Earth, Mars, Jupiter, Saturn.
Exactly those 6. He proposed explaining their spacing using only 5 geometric shapes, the Platonic solids.
Just 5 shapes for the whole structure?
Just 5. He pictured them nested inside each other, like Russian dolls, with spheres separating them, marking the orbits.
Wow.
And when you hear that now, it sounds more like Pythagorean theology mixed with geometry than, the foundation for modern physics.
It absolutely does. It sounds almost mystical.
It does. And we really need to understand the powerful historical and, crucially, theological context that made this seem not just plausible, but like the most beautiful and logical truth imaginable at the time.
Okay, let's dig into this geometric vision then, because when you read about it, it's absolutely captivating. The sheer ambition and, the elegance of it.
It really is.
This whole idea centered around a publication, right? Back in 1596, a book called Mysterium Cosmographicum.
That's the one, the cosmic mystery.
Which is quite a title. And the mission of this book was, monumental.
Oh, absolutely.
Kepler wasn't just trying to chart the paths of the planets like others were doing. He wanted to explain the reason for the precise gaps, the spacing between the known orbits of those 6 planets.
Well, why those specific distances? Not just what they are.
Exactly. Why were they spaced just so? He wasn't just mapping the house. He was trying to reveal the precise divine scaffolding holding the whole thing up.
And the foundation for this scaffolding, the material he thought God used, was incredibly old, deeply revered, and just packed with philosophical weight, the 5 Platonic solids.
Okay, so remind us, what are these shapes exactly?
Right, so these are the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. They're special because they're the only 5 convex polyhedra where all the faces are identical regular polygons.
Like squares on a cube or triangles on a tetrahedron.
Exactly. And the same number of faces meet every single vertex, every corner. They are, in a sense, the definition of geometric perfection, pure symmetry.
And these weren't just abstract shapes to him or to people before him.
Not at all. Philosophers and theologians going way back to ancient Greece. Plato especially, in his dialogue, Timaeus had actually associated these 5 shapes with the fundamental elements of the universe.
Really? How so?
Well, Plato linked the cube with earth, the octahedron with air, the tetrahedron with fire, the icosahedron with water.
Okay.
And the 5th one, the dodecahedron, he associated with the cosmos itself, the heavens.
Mm-hmm.
So for centuries, they were considered these absolute fundamental building blocks of reality, divine shapes.
Wow. Okay, so that adds a whole layer of meaning.
The massive layer. And this is where Kepler's genius and also his eventual beautiful misstep comes in. His central mechanism was structurally brilliant, even if it turned out to be wrong.
So how did he use them? He didn't just say they exist.
No. He took these 5 shapes and used them to physically nest spheres. You have to picture it. Imagine a huge sphere representing the orbit of Saturn, the outermost known planet then.
Okay, got it.
Inside that sphere, he places a cube, fitting snugly. Inside that cube, he nests the sphere for Jupiter's orbit. Inside that sphere, he puts the tetrahedron.
And then the sphere for Mars.
Exactly. And so on down through Earth, Venus, and Mercury, using the dodecahedron and icosahedron in there too.
So 5 solids providing the spacing for 6 planets.
Precisely. By arranging these 5 solids in a specific, very deliberate order, which, importantly, he figured out by trial and error, trying to match the known distances.
Oh, okay.
He created these geometrical shells, and these shells, he claimed, aligned perfectly with the orbital paths of the 6 known planets.
Oh.
It was a model driven entirely by pure geometry.
And underpinning all this was a core philosophical belief.
Absolutely immutable for him. He believed that a divine creator, being perfect and all-knowing, must design the universe based on absolute geometric simplicity and harmony.
God as the ultimate geometer.
That's exactly the idea. God would use perfect tools. If God was the architect, he wouldn't rely on, sloppy, imprecise measurements or complicated mathematical hacks and workarounds.
Like the epicycles in the old system.
Precisely like the epicycles. God would use the most perfect, fundamental building blocks available. And given the intellectual tradition, stretching back to Plato.
Those perfect building blocks had to be the Platonic solids.
They had to be. It seemed almost self-evident to him.
Now, what's crucial to understand, as you mentioned, is why he was initially so convinced he'd actually cracked the code of creation. This wasn't just a nice idea he had, right?
No, far from it. This wasn't pure speculation in his mind. He had evidence, or what seemed like evidence, that appeared to confirm his bias.
What kind of evidence?
Well, based on the relatively imprecise measurements available in the late 16th century, often data inherited from Copernicus or even older sources.
Right, pre-telescope data. Yeah.
Exactly. Pre-telescope, often naked eye observations. Early comparisons of the ratios between the orbits, particularly of the ratio between Mercury and Venus, seem to match his geometrical theory surprisingly well.
So the numbers, rough as they were, seem to line up with the shapes.
They seem to line up remarkably well in some cases, not perfectly across the board, but well enough.
That must have been an absolutely earth-shattering moment for him. I mean, here he is, this young, brilliant, deeply religious scientist, finding that the messy reality of planetary orbits, or at least the best approximation they had, aligns almost perfectly with the most fundamental, beautiful shapes geometry has to offer.
You can see why he'd be convinced.
It's enough to convince anyone they've stumbled upon the actual divine blueprint for the cosmos.
Totally. He felt he was reading the mind of God.
But hang on, I have to stop and ask about this. You said he nested them in a specific, deliberate order. Was there some inherent philosophical or geometric reason for that specific sequence, like cube first, then tetrahedron or whatever it was? Or was it just what fit the numbers?
That's a fantastic, really probing question, because the order was crucial, and it reveals a lot about his method. He didn't just stack them randomly like kids' blocks.
Right.
Kepler tried different arrangements. He sought an order that mathematically worked, or seemed to work, to approximate the known planetary distances.
So the data, even the rough data, was guiding the order.
It was guiding the order. For instance, he found that nesting the octahedron between the orbits of Venus and Earth and the icosahedron between Earth and Mars gave ratios that were pretty close to what Copernicus had calculated. The ancient sources, the philosophy, didn't dictate this specific stacking order. The observed astronomical distances did, albeit approximately, but the very fact that he found an order that seemed to fit so well.
That confirmed his belief.
It totally affirmed his belief that he was simply uncovering the divine choice. He wasn't inventing the system, you see. He believed he was revealing God's pre-existing beautiful design.
He was trying to reverse engineer God's architectural plan.
That's a perfect way to put it. Exactly. And to really appreciate the sheer magnitude of this pursuit, we have to look beyond just Kepler the mathematician. We need to see Kepler the man.
His personal context.
Yes, because his context, his life, his other roles heavily informed his scientific decisions. It wasn't happening in a vacuum.
Right.
Our sources really emphasize that his identity was complex and often frankly, tumultuous. He was far more than just a scientist in the way we think of it today.
He wore many hats.
Many hats indeed. He was a trained astrologer, which, we might dismiss now, but back then it was an essential, often lucrative part of his livelihood. He needed to cast horoscopes to make ends meet sometimes. He was also a husband, a father who suffered the loss of children, and, crucially, a deeply religious Lutheran man living through a time of intense theological conflict and upheaval. The Counter-Reformation was raging.
So a lot going on personally and politically.
A huge amount. And all these identities shaped his worldview. They made the study of the cosmos not just an intellectual puzzle, but a profound religious quest, a way to find certainty, order, and maybe read the unchanging mind of the Creator in a chaotic world.
And that deep religiosity, that quest for divine order, directly informed his scientific rejections too, didn't it? Particularly his strong distaste for the old, complex, Earth-centered model, the geocentric system.
Oh, profoundly. He couldn't stand it.
That model, inherited from the ancient astronomer Ptolemy, had reigned supreme for, what, over 1,000 years?
14 centuries, pretty much unchallenged in Europe.
And it relied heavily on these things called epicycles. Can you just quickly remind us what an epicycle actually was and why Kepler found it so theologically offensive?
Absolutely. So the core problem for the geocentric model was observation. The ancients believed celestial bodies must move in perfect circles, because the circle was seen as the most perfect divine shape, and heavens were perfect.
Okay, divine circles.
Right. But observations, even ancient ones, clearly showed that planets don't move smoothly across the sky. They sometimes appear to slow down, stop, and even move backward for a bit. That's called retrograde motion.
Which doesn't fit a simple circle around the Earth.
Not at all. So to save the phenomena, to make the observations fit the perfect circle theory, Ptolemaic astronomers introduced epicycles. Imagine a planet moving on a small circle.
Okay.
And the center of that small circle moves along the circumference of a larger circle, called the deferent, which is centered near the Earth.
So circles upon circles, loops.
Exactly. Loop the loops in the sky. And the problem was, as observational data got just a little bit better over the centuries, they needed to keep adding more and more complexity. More epicycles, offset centers called eccentrics, and another fudge factor called the equant.
It sounds really complicated.
It was incredibly complicated. The whole Rube Goldberg contraption of circles, just to make the predictions roughly match what people saw.
And Kepler looked at this system.
And he was repulsed. For Kepler, this convoluted, messy, patched-together system was fundamentally inconsistent with his idea of a universe created by an elegant, precise, and simple God.
It lacked beauty, lacked divine simplicity.
It utterly lacked it, in his view. It suggested a kind of slapdash, last-minute cosmic repair job, rather than a masterful, unified divine plan.
So the question for him became, why would a perfect God rely on such complex, clumsy, inelegant corrections just to keep the Earth, which, in the Christian worldview, was a mundane, flawed, sublunar place stuck awkwardly at the center?
Exactly. It just didn't make theological sense to him. It sounds like, initially at least, the theological driver was perhaps even stronger than the purely empirical one in pushing him away from geocentrism.
It seems that way.
It really does. And this strong theological preference pushed him firmly toward the alternative, the sun-centered or heliocentric model proposed by Copernicus decades earlier.
But it wasn't just a scientific switch for him, like choosing a better calculator.
No, not at all. It was a deeply spiritual alignment for Kepler. He embraced heliocentrism for both scientific and theological reasons.
Oh, so theological.
He saw the sun as a powerful physical and metaphysical symbol. It was, for him, an analogy for the Christian Godhead, the source of all light, all heat, all motion, all life in the solar system.
The prime mover, almost.
In a very real sense, yes. This made the sun the only appropriate and theologically sound center for the cosmos in his mind. It was the dynamic engine, the source of vitality, and therefore it had to be the geometric heart of creation. His cosmology wasn't just science, it was literally a form of worship, an attempt to understand God's glory.
Which brings us back to the Platonic solids. We can't forget the historical weight they carried.
Absolutely crucial. They weren't just interesting mathematical shapes he happened to like. They carried this immense intellectual authority, this sacred meaning built up over centuries. So when Kepler claimed that by nesting these 5 specific solids, the cube, tetrahedron, and so on, he was accurately mapping the planetary orbits.
He wasn't just making a mathematical claim?
No. He was, in effect, proving, so he thought that God used the very language of geometry that humans had recognized as sacred for millennia. It lent his Mysterium Cosmographicum theory this massive philosophical and theological weight. It made it feel profoundly, eternally true.
It connected his science directly to ancient wisdom and divine principles.
Perfectly put. And we also have to layer in, just briefly, the personal context again. Kepler's own life was often incredibly difficult, marked by instability.
You mentioned that.
Yeah, he faced political turmoil due to religious wars, constant financial worries, moving from job to job, city to city. Perhaps most famously, later in his life, his own mother was accused of witchcraft.
Seriously?
Oh yes, he had to spend years, huge amounts of energy and money, mounting a complex legal defense to save her from being burned at the stake. He eventually succeeded, but it was a harrowing ordeal.
Wow. I had no idea.
So in the face of all this earthly chaos, this personal turmoil and societal upheaval, you can see why Kepler might have been almost desperate to find cosmic order. Perfect, unchanging, predictable order in the heavens.
An escape, almost. Or a source of stability.
Perhaps both. The Mysterium Cosmographicum, his geometric model, was his attempt to find that stable, unchanging, perfect framework for the universe. It was an intellectual sanctuary.
And he genuinely believed he'd found it.
He truly believed he'd cracked the code of creation. And for a little while, the initial approximate data available seemed to affirm his monumental discovery. But, and this is the huge pivot in the story,
There's always a but in science.
there usually is, because the scientific theory, no matter how beautiful, no matter how theologically satisfying, must eventually confront the brutal, uncompromising reality of data. Precise data.
Okay, so Kepler has this elegant, beautiful, divinely inspired geometric model, the Mysterium Cosmographicum. It feels complete, it feels right to him. But as our sources really stress, it had this critical flaw, didn't it? It lacked concrete, unimpeachable empirical proof.
That was the Achilles heel. The data he used initially, the Copernican data, was good for its time, certainly better than Ptolemy's. But it just wasn't high resolution enough.
Not precise enough.
Not precise enough to definitively confirm a cosmic truth that held up perfectly across all 6 planets, especially the tricky ones like Mars. There were discrepancies he kind of had to fudge or explain away.
And the universe, as you said, doesn't negotiate based on how beautiful your theory is.
Not one bit. And that gap, the lack of truly precise, meticulously measured reality, is what led to the most critical and famously turbulent partnership in Kepler's life. His relationship with the great Danish observer, Tycho Brahe.
Ah, Tycho, the man with the golden nose and the data.
That's him. Tycho Brahe was a phenomenon in himself, a flamboyant Danish nobleman who, through royal patronage, possessed his own private island observatory, Uraniborg.
An entire island dedicated to stargazing.
Pretty much. And he was absolutely obsessed, fanatically so, with accurate measurements. He designed and built the largest, most precise astronomical instruments before the invention of the telescope.
So he had the best data.
He possessed the most precise, most comprehensive pre-telescope astronomical data ever amassed in human history up to that point. For years, decades even, he and his assistants had meticulously recorded the positions of the stars and, crucially, the planets with unparalleled accuracy.
And this data was the missing ingredient Kepler desperately needed.
It was the ultimate test for his divine geometry. Could the beautiful theories survive a confrontation with the best possible measurements of reality?
So you have this ultimate intellectual pairing, right? But also, as history tells it, a really volatile one.
Oh, incredibly volatile. You had Kepler, the profound theoretical visionary, the pattern seeker, convinced of underlying harmony.
Meeting Brahe, the empirical titan, the master observer who trusted only the numbers, the hard data, but maybe lacked the mathematical horsepower or theoretical framework to synthesize it all himself.
Exactly. Brahe had his own cosmological model, sort of a hybrid Earth-Sun system, that he wanted his data to support.
And Kepler essentially went to work for Brahe in Prague around 1600.
That's right. Brahe had become the imperial mathematician to the Holy Roman Emperor Rudolf II in Prague, and he needed help analyzing his mountain of data. He invited Kepler.
But their relationship, as the sources detail, was fraught with tension from the start.
Absolutely. Brahe was known to be, shall we say, a prickly character, egotistical, secretive, fiercely protective of his life's work. He hoarded his precious data like a pirate hoarding treasure.
Didn't want Kepler to steal his thunder.
Precisely. He knew how valuable his observations were, And he was hesitant, apparently very hesitant, to give Kepler full access, fearing Kepler would use it to promote the Copernican system or develop some new theory that would overshadow Brahe's own contributions.
So a partnership of mutual distrust, almost.
And mutual necessity. It was really a marriage of convenience. Brahe needed Kepler's unmatched mathematical genius to make sense of his decades of observations.
And Kepler absolutely needed Brahe's data to truly validate, or, as it fatefully turned out, to destroy his cherished Platonic model.
Yeah. And famously, Brahe didn't give Kepler the keys to the kingdom right away. He assigned Kepler the most difficult, most challenging problem, figuring out the precise orbit of Mars.
Why Mars?
Because Mars's orbit was known to be particularly troublesome. It deviates most noticeably from a simple circle. Brahe probably figured Mars, with its highly eccentric path, would keep Kepler bogged down for years, maybe prevent him from quickly confirming Copernicus or dismantling Brahe's own model.
A clever, if somewhat cynical, move.
Perhaps. But then history takes a sharp turn. Brahe died suddenly, unexpectedly in 1601, after less than 2 years of working together.
And Kepler.
Well, Kepler, through a combination of, let's say, legal maneuvering, sheer determination, and perhaps some actions that were ethically questionable by modern standards,
He got the data.
he essentially secured control over Brahe's entire treasure chest of recorded observations after Brahe's death. Some accounts suggest he basically refused to let Brahe's heirs take it, arguing it belonged to the emperor or was essential for his ongoing work.
Wow, so now he had it all. Years and years of painstaking reality now in the hands of the most determined pattern seeker in Europe.
The ultimate data set. And this data, particularly those high-resolution Martian observations that Brahe had meticulously recorded night after night, this is what led to the devastating realization for Kepler.
The moment of truth.
The moment of truth. After years, literally years, of painstaking calculations, trying every conceivable geometric trick, desperately attempting to force the observed positions of Mars to fit some variation of a perfect circular orbit, Kepler faced an intellectual crisis of profound magnitude.
He couldn't make it fit.
He could get close, agonizingly close, but not perfect. And this is where we absolutely have to talk about the famous 8 minutes of arc.
Right, this feels like the crux of the whole story.
It really is. You could argue it's one of the defining moments, maybe the defining moment, of the entire scientific revolution, because it represents the precise point where human belief, mathematical elegance, and theological preference finally bowed to the stubbornness of observed reality.
So what were these 8 minutes of arc?
Kepler tried, according to his own writings, something like 70 different variations of circular orbits for Mars, adjusting centers, speeds, using every tool in the Ptolemaic and Copernican toolkit. He finally found one model, his best circular attempt, that still deviated from Brahe's measured positions of Mars by up to 8 minutes of arc at certain points in its orbit.
Okay, how big is 8 minutes of arc? Help us visualize that.
It's tiny, really tiny. There are 60 minutes in 1 degree of angle and 360 degrees in a full circle. So 8 minutes is 8/60ths or 2/15ths of a single degree.
That sounds almost negligible. Can you even see that difference?
That's the crucial point. It was smaller than the uncertainty typically associated with naked eye observations before Brahe. Historically, almost any other astronomer would have just ignored it.
How so?
They would have blamed it on measurement error, atmospheric distortion, imperfections in the instruments, anything they would have rationalized it away to save the beautiful, teal-old theory of the perfect circle. Circles had to be right.
But Kepler didn't.
Kepler couldn't, because he had such profound respect, almost reverence, for the incredible precision and integrity of Tycho Brahe's measurements. He believed the data was that good. He trusted Brahe's numbers more than he trusted the axiom of perfect circles.
And he famously wrote about this, didn't he?
He did. He wrote something to the effect of, "If I had believed that we could ignore these 8 minutes of arc, I would have corrected my hypothesis, the circular orbit, accordingly. But," he continued, "because it could not be done, these 8 minutes alone have led the way to the complete reformation of astronomy."
Wow, these 8 minutes alone.
Think about the internal struggle that implies, the sheer intellectual honesty required. He was forced by this tiny discrepancy to conclude that his beautiful, harmonious, geometrically perfect, divinely sanctioned model of the Mysterium Cosmographicum and the foundational belief in circular orbits simply didn't fit reality.
That must have been devastating.
Absolutely devastating. Imagine dedicating your entire early career, your intellectual prime, to a theory you believed was divine truth itself, the key to the cosmos. only to have the best data available definitively, stubbornly refute it, and by a margin almost invisible to the naked eye,
Most people would have probably given up or fudged the data.
or doubled down on the theory. But this is where Kepler's character, his scientific spirit, truly shines. Instead of clinging desperately to his preferred theory, his beautiful Platonic solids, he adapted.
He changed his mind based on evidence.
He changed his mind based on 8 minutes of arc.
Yeah.
This willingness to scrap his deepest, most cherished, theologically preferred idea in favor of a minute but persistent empirical detail that is the critical action. That intellectual humility, that defining marker of the true scientific spirit, is what separates a dogmatic philosopher from a genuine scientist.
He abandoned the pursuit of superficial perfection.
And followed the data, no matter how inconvenient, no matter how ugly or complex the path seemed. He followed where the numbers led.
And this profound intellectual humility, this painful but necessary rejection of the Platonic model and the ancient ideal of the perfect circle, this is what led directly, wasn't it, to the formulation of the real Kepler's laws of planetary motion.
Exactly. The things he's actually famous for today.
The 3 laws that truly cemented his legacy, blew up the old models, and served as the absolutely essential foundation for Isaac Newton's theory of universal gravitation decades later.
Without Kepler's laws, there's arguably no Newton's Principia. They described how the planets moved, which Newton then explained why.
So the journey started with this profound belief in perfect circles defined by perfect solids.
The Mysterium.
But the hard Martian data forced him to abandon the circle and explore a different, perhaps less intuitively perfect shape, which brings us straight to Law 1, the shape of orbits.
Right. The elegant, divine perfection of the circle simply had to go. It didn't work.
Yeah.
Kepler spent years after accepting the 8-minute discrepancy, wrestling with the Mars data, trying other shapes, ovals, egg shapes.
Really? He tried other curves.
Yes.
Yeah.
Spent ages on ovals.
Yeah.
But eventually, through sheer mathematical perseverance, he realized that the actual path of the planet wasn't a circle, wasn't an oval, but a specific, precise mathematical curve. An ellipse.
An ellipse. A stretched circle, essentially.
In simple terms, yes. And this might seem like just a small geometrical tweak moving from a circle to an ellipse,
Okay.
but it was a monumental conceptual revolution. It meant abandoning that millennia-old philosophical and theological insistence on perfect celestial motion. The heavens weren't moving in perfect circles after all.
And there was another crucial detail in that first law about the sun's position.
Absolutely critical. He found that the sun is not positioned in the geometric center of that ellipse. Instead, the sun sits at one focus of the ellipse.
Okay, explain the focus part. An ellipse has 2, right?
Exactly. If you imagine drawing an ellipse using the classic pins and string method, you stick 2 pins in a board, loop a string around them, and trace the curve with a pencil held taut against the string.
Yeah, I remember doing that in school.
Those 2 pin locations are the foci, the plural of focus. Kepler found that the sun resides at one of those 2 focal points, with the other focus being empty space.
What's the significance of putting the sun there at a focus rather than the center?
It's huge. It completely redefined the geometry of the solar system. It meant the distance between the planet and the sun is constantly changing throughout the orbit. And perhaps more profoundly, it suggested the sun wasn't just a passive geometric center or even just a spiritual center. It was somehow physically involved in the planet's motion. It was positioned at a dynamically special point.
Setting the stage, conceptually at least, for the later idea of a force emanating from the sun, like gravity.
Precisely. It hinted at a physical connection, a dynamic relationship governed by the sun's position, that the old centered circle models completely lacked. It broke the symmetry.
Okay, so Law 1. Planets move in ellipses with the sun at one focus. That nails the shape. The second law then tackles the dynamics of that orbit, right? It moves away from the old idea of constant uniform speed. That's Law 2, equal areas.
Exactly. The planets aren't just moving in ellipses, they're moving at varying speeds within those ellipses. Law 2 describes the mechanism beautifully. It states that a line segment connecting a planet and the sun sweeps out equal areas in equal times.
Okay, equal areas and equal times. Let's unpack that. What does it look like?
Imagine that line segment connecting the sun at its focus to the orbiting planet. Think of it like a long broomstick sweeping across the orbital plane as the planet moves.
Got it, a cosmic broomstick.
A cosmic broomstick. Law 2 says that no matter where the planet is in its elliptical orbit, that broomstick sweeps the exact same amount of area in, say, 1 month.
The area swept is constant over a fixed time.
The area swept is constant. Now, what does that mean for you, the listener, in terms of the planet's speed? Remember, the orbit is an ellipse, so the planet's distance from the sun is constantly changing.
Right. Sometimes closer, sometimes farther.
So when the planet is closer to the sun at its closest point, called the perihelion, that imaginary broomstick line is shorter. To sweep out the same area in 1 month when the line is short, the planet has to travel a much greater distance along its orbital path. It has to move faster.
Huh. Okay. Shorter radius means faster angular speed to cover the same area.
Exactly. And conversely, when the planet is farther away from the sun at its farthest point, the aphelion, the line segment, is longer. So to sweep out that same standard area in 1 month, the planet travels a shorter distance along its orbit. It moves slower.
So planetary motion isn't uniform or constant at all, as everyone had assumed for centuries.
Not remotely constant. The planet continuously speeds up as it approaches the sun and slows down as it recedes. Its velocity is always changing, but in a predictable, mathematically defined way related to area.
The universe suddenly seems much more dynamic, less like a perfect clockwork. Variable speeds, governed by distance from this central point, the sun, that must have been incredibly disruptive to the old paradigm of perfect, steady, harmonious celestial motion.
Hugely disruptive. It replaced a kind of static geometric harmony with a dynamic physical mechanism. The elegance shifted from the shape itself to the mathematical relationship governing the motion.
Okay, law 1 is shape, ellipse, sun at focus. Law 2 is dynamics, equal areas, variable speed. What of the third one that came later, right?
It did, yes. It took him quite a few more years of searching for deeper harmonies. This is Law 3, the proportionality law, sometimes called the harmonic law.
Harmonic law sounds like he was still searching for that cosmic music.
He absolutely was. Even after abandoning the Platonic solids, he never gave up the belief that the universe was fundamentally harmonious and based on mathematical relationships. He just found the harmony in a different place.
So what does law 3 state?
This one is the most purely mathematical, and it's incredibly powerful because it connects the orbits of all the planets together in a single overarching framework. It relates how long a planet takes to orbit the sun to how far away it is.
Okay.
The relationship states that the square of the orbital period, that's p, the time it takes the planet to complete one full orbit, its year, is directly proportional to the cube of the semi-major axis of its orbit. That's a, which is essentially the average distance from the sun.
So p squared is proportional to a cubed. $2 propto a33.
That's the one. 2p taller propto a33.
Let's make sure we break that down. What does 2p taller propto a33 actually mean in practice for someone listening? Why is that specific mathematical relationship so critical? It sounds a bit abstract.
It does sound abstract, but its consequence is profound. It means that the farther a planet is from the sun, the disproportionately, ridiculously longer its orbit takes. It's not a simple linear relationship. Double the distance doesn't mean double the time.
Okay, how does the math work out? Give us an example.
Okay, well, roughly speaking, Jupiter is about 5 times farther from the sun than Earth is. So A is 5 times bigger.
Right.
According to Kepler's third law, you have to cube that distance factor. 5 cubed is 5 by 5 by 5 by 5, 125, and then take the square root to find the factor for the period. The square root of 125 is about 11.2.
So Jupiter should take about 11.2 Earth years to orbit the sun.
And it does. Jupiter's orbital period is just under 12 Earth years. The law works beautifully. If you know a planet's average distance, you can calculate its orbital period, or vice versa for any planet, using this exact same proportional relationship.
Wow. So it locks the whole solar system together into one mathematical structure.
Precisely. It reveals the underlying mechanical architecture of the entire system. This law was the last of the 3 to be discovered and published. It finally appeared in his 1619 work, Harmonices Mundi.
Harmony of the World. The title is so telling, isn't it?
It really is, even after being forced to abandon the simple, visually beautiful geometry of the Platonic solids from Mysterium Cosmographicum.
He was still searching for cosmic harmony.
He never stopped. But now he found it not in those perfect, almost arbitrary shapes, but in these precise, quantitative, mathematically verifiable physical laws that govern the actual motion. He replaced a kind of superficial elegance with a much deeper, functional, mathematical harmony.
So just to synthesize that incredible shift then, he starts with the Mysterium, trying to explain why the planets were spaced using divine geometry.
Right, a static model based on shapes.
And ends up, through brutal confrontation with data, formulating 3 laws that provide an accurate, physics-based, mechanical description of how the planets actually move ellipses, changing speeds, all locked together by 2p dollar propto a33.
That's the journey. He replaced an elegant but wrong why with a functional, predictive, and ultimately correct how. And that intellectual shift, driven by empirical evidence, is his true, enduring legacy. It paved the way for physics as we know it. And Kepler's whole journey, this arc from Mysterium to the laws, offers really profound lessons that go way beyond just astronomy. It tells us a huge amount about ourselves, about how we think.
How so?
Well, for one, it's a powerful illustration of the limits and also the strengths of the pattern-seeking human brain.
Ah, our tendency to see patterns everywhere.
Exactly. We seem to be neurologically wired, psychologically driven, to find order, symmetry, meaning, and causal links in the world around us.
Yeah.
It's a survival mechanism, probably.
Right. Helps us make sense of things, predict things.
But it can also mislead us. That's why those initial near matches between the geometry of the Platonic solids and the rough orbital radios available to Kepler were so incredibly compelling to him. His brain desperately wanted to see that beautiful, simple pattern.
And it found something close enough to latch onto.
Precisely. The human desire for order, for elegance, for a neat story, can easily make us see patterns in noise, mistake coincidence for cosmic significance, or premature confirmation for final proof. Kepler found a pattern that was almost true.
And his whole belief system, his theological framework, told him that this almost truth must be the perfect truth he was seeking.
Right. And the scientific spirit, maybe the discipline that Kepler ultimately embodied, is the rigor required to question those compelling patterns, to test them against the hardest evidence, and to tell the difference between a beautiful illusion and a maybe less beautiful but verifiable reality.
Which brings us right back to the value of bold mistakes.
Yes, that's another huge takeaway here. Scientific progress, as Kepler's story shows so dramatically, doesn't always follow a neat, logical, straight line from question to answer.
It's not usually step-by-step incremental.
Often it's not. Sometimes, maybe often, it comes from making grand, bold, ambitious mistakes, hypotheses that are imaginative, specific, and crucially testable.
Like the Mysterium Cosmographicum. It was wrong, but it was specific.
Exactly. Mysterium Cosmographicum was fundamentally wrong about the structure of the solar system. But because it was such a specific, ambitious, and ultimately testable hypothesis, the gaps match these nested solids. It forced Kepler onto the path of seeking superior data. Brahe's data. And confronting that data then forced him, eventually kicking and screaming almost, to pursue entirely new ways of thinking about orbits, to abandon circles, and to develop the complex mathematics needed to calculate ellipses accurately.
So the wrongness of the first idea was actually productive.
Incredibly productive. If he had proposed just a vague, fuzzy theory about divine harmony, he might never have felt the intense need for Brahe's ultra-precise measurements. He certainly wouldn't have spent those agonizing years trying desperately to reconcile a perfect circle with the stubborn reality of the Mars data down to 8 minutes of arc.
It was that sustained pressure, the beautiful hypothesis grinding against the hard empirical data that ultimately catalyzed the revolution.
Yes. It required immense intellectual stamina, incredible mathematical skill, and as we discussed, arguably one of the greatest acts of scientific humility in history to finally break through.
Which leads, I suppose, to the ultimate definition of science that Kepler came to exemplify.
I think it does. His willingness at the end of the day to scrap his most cherished idea, the mysterium, the theory that brought him his initial fame, the one that felt so right, so divinely affirmed.
To throw it away.
To throw it away, or at least fundamentally revise it, purely because it conflicted with the best empirical data he could get his hands on. That's the core ethos, isn't it?
It seems like it.
It's the rejection of personal preference, of aesthetic bias, even of deeply held theological conviction in favor of what the evidence, carefully collected and rigorously analyzed, actually dictates. Even when that evidence is messy, inconvenient, or forces you to accept something as aesthetically unsatisfying, perhaps, as a stretched-out circle instead of a perfect one.
Wait, I have to circle back to that theological question again, just to be really clear, because I think it's key. Why was accepting a stretched circle and ellipse ultimately easier for his religious conscience than accepting the geocentric system's messy epicycles? Both seem like deviations from perfect simplicity.
That is the perfect question for comparison. It gets right to the heart of his motivation. The key difference, I think, lies in the nature of the messiness or the complexity.
Okay.
The epicycles felt arbitrary to him. They were mathematical patches, ad hoc fixes layered upon layer, seemingly without a single unifying physical rationale. They felt contrived, engineered, like adding gears to fix a faulty clock, rather than revealing an underlying principle.
This fix is not fundamental truth.
Exactly. The ellipse, however, while maybe less perfect than a circle in the ancient sense, had its own profound mathematic elegance, and critically, its specific shape and the planet's motion along it were rigidly dictated by a clear physical relationship, the sun's position at the focus and the law of equal areas.
So it wasn't arbitrary complexity.
It wasn't arbitrary complexity, it felt like a complex truth. He discovered that the universe was governed by fixed, elegant, discoverable mathematical laws, even if the basic geometric shapes weren't the Platonic solids he initially expected. He essentially replaced a superficial visual perfection with a deeper, functional mathematical harmony. God's artistry was in the laws of motion, not just the static shapes.
That makes sense. The elegance shifted to the physics, to the mathematical relationships.
Yes, he could still see God's mind at work, just in a different, more dynamic, and ultimately more accurate way. Hashtag tag outro.
What a monumental journey we've traced. I mean, Kepler starts out searching for this divine blueprint, literally trying to fit the cosmos into 5 perfect shapes left over from ancient Greece.
A beautiful, compelling idea.
But his own rigorous honesty, his commitment to matching theory with the best possible observations, forces him to confront the truth. The universe actually operates using these, well, less intuitively perfect ellipses, with planets constantly changing speed, all governed by precise mathematical proportions linked to physical distance. His spectacular, bold, beautiful failure, the Mysterium, directly paved the way for his revolutionary, correct laws. It really demonstrates that failure is often the first, maybe the most necessary, step toward truth in scientific exploration.
It's such a powerful lesson. And it leads to a final thought, maybe a challenge for everyone listening.
Okay.
As we close out this deep dive, maybe take a moment to consider this in your own work, your own field, or even just your life. What fundamental beliefs, what elegant models or assumptions do you currently hold? Things that feel right, that seem obviously true, whether it's in your professional field, your understanding of history, politics, or even just how the world works.
Okay.
That might just possibly be shattered or at least radically revised if confronted with superior, perhaps inconvenient, contradictory data.
That's a challenging question.
It is, and the follow-up is, do you possess or can you cultivate Kepler's willingness to adapt? That courage to revise your most beautiful, most cherished theoretical structures and embrace the messy, perhaps less elegant reality of the ellipse when the evidence demands it.
Because that willingness to change.
That willingness to change your mind in the face of evidence, rather than the initial discovery of the right shape or answer, is perhaps the enduring universal lesson from the great astronomer Johannes Kepler. It's the heart of the scientific spirit.